Hello everyone, my name is Mark Lee, and today I'm going to be doing a lecture on summations in probability. So this lecture is going to be founded upon one problem, and that is, what is the average number of six-sided dice rolls needed to get a 6? Now this problem is from a notable book in probability called 50 Challenging Problems in Probability, and this is question 4 among the 50 problems. Now, basically what this problem translates down to is, how many times do I need to roll a six-sided dice in order to get the first 6? And the answer seems intuitive. Of course, it's 6 dice rolls because the probability that you roll a 6 on each dice roll is 1/6, and therefore, in order to get a 6, you should roll the dice 6 times so that the average probability is 1. It seems intuitive. And our friend Einstein kindly says, duh, because it's so incredibly obvious. But then I ask you why this is. I ask you for a detailed proof. And proving this problem actually requires some advanced mathematical concepts, and we are going to start exploring them. So the first concept that we need to explore in order to be able to prove this conjecture is the binomial distribution. Now, what the binomial distribution is, it's basically a repeated probability distribution of repeated trials of the same outcomes, as you will. So, for example, this includes dice rolling or sampling with replacement. Note here we have to have it with replacement, because if we do it without replacement, then the probability field alters each time. So sampling with replacement, that way the probability stays the same, because whatever we draw out of the box gets replaced in the box, and therefore no changes in the actual probabilities of each outcome occur. And basically, this is the formula for the binomial distribution. What this means is that the probability that the outcome will happen x times is n combination x px 1 minus p to the power of n minus x, where n is the total number of trials, px is the probability of x successes in n trials, p is the probability of success for each trial, and x is the number of successes we want. So for example, with the example, by the way, this is the symbol of the binomial distribution. With the example of the dice, for example, if our chosen outcome, what we consider a success, would be to roll a 6, p would be 1/6, n would be the number of times we would have to roll the dice, and x would be the number of times that we do get a 6 after rolling the dice. Now, there's some properties that we want to go over for each binomial distribution. So basically, there's variability. So people also call this variance. It's one of the standard metrics of how varied a data set is, the range of variations that the values contain. And here in a binomial distribution, let's refer back to the above formula. Variability Vx is npq, where q is basically a substitute for n minus p. And this leads us to the standard deviation, which is basically just the square root of the variance. So, I did not see it fit to include another separate formula here. Meanwhile, the expected value of a variable of a binomial distribution is E of x is np. And this is basically where our conjecture starts. The idea that NP allows us to assume that the number of trials required and the probability should be reciprocals of one another. But there's more to go about proving this than just saying that E of x is NP. And then there's the binomial theorem, which is not terribly relevant to the binomial distribution, but it still constitutes one of the cornerstones of mathematics in general. So here it is. This is the binomial theorem, and it basically allows us to convert the sum of all of these probabilities, seen here in the formula, to this nice, basically a binomial expansion where x and y have been grouped together and exponentially increased by n. And what this entails in terms of the earlier formula is that since here x and y add to 1, x plus y is 1, and therefore the total sum of the probabilities is 1, which is, of course, something trivial that we know about every single probability distribution out there. Now, let's do a couple of sample problems. The first one is, John guesses on all 30 problems in a 5-answer multiple choice quiz. Now, what is the probability that he will have gotten exactly 10 problems right? Now, obviously, in the internet format, it is much harder for me to actually go about solving this problem. But basically, the key to this problem is recognizing the different parts of the binomial probability formula and then inputting the values into the formula. So here, for example, n is 30 because there's a total of 30 problems that are going to be attempted. Now, since it's a 5-answer multiple choice quiz and John guesses randomly on each problem, that would mean that the possibility that he gets a problem right would be 1 over 5. So we have our value for p. And meanwhile, since we want John to get exactly 10 problems right, that would indicate that the number x is 10, because that's the number of successes we want in the total n equals 30 trials that we're going to have. And this leads us to the answer of 0.0355. So I'm guessing John isn't going to be doing very well on his multiple choice quiz. Meanwhile, the second problem is about Felicity, and she is rolling a 6-sided die 90 times, and we want to calculate the expected value and standard deviation of the number of times she will roll a number 1. And again, basically this is a simple inputting mathematics problem where we find the different constants. So here n is 90. Since it's a 6-sided die and the chance of the die rolling is completely random unless the die is fixed, which it is not here. Since it's a random die, we can assume that p will be 1 over 6, that there's only one number that we want. And using n and p, we can then go about calculating the expected value and the standard deviation, which, if you remember, is the square root of the variance, and the variance is npq. But since q is 1 over p, if we have n and p, we can calculate all of the values, leading us to the expected value of 15 die rolls with the number 1 and a standard deviation of about 3.54 die rolls. Another concept that we need to master before we go about solving the problem is infinite geometric summations. Basically, we need to look at what a geometric series is first. Basically, what a geometric series is a series of numbers where you start with the first term, which is a, and then the next term, every next term after that is the term before it times the common ratio, which is r. So an actual geometric series starting with a and with common ratio r would go something like a, ar, ar squared, ar cubed, etc. And now we look at the geometric summation formula. Now, originally, we were going to prove this, but again, the internet format is a little bit restrictive when it comes to how much we can actually prove. So basically, this is the geometric summation formula, and the way we can go about this, and this will be somewhat important later, is we can basically say that S is the sum of a plus ar squared, a plus ar squared plus ar cubed, etc., etc., etc. And then what we can say is that we can multiply r to s, giving us rs equals r plus, ar plus ar squared, basically the same geometric series, just without the a. And what this allows us to do is basically subtract the two formulas that we have, and then that gives us an equation that allows us to find s in terms of a and r. It's actually an ingenious type of formula, so I encourage you to look more into the actual proof of it. It's not very complicated. But basically, this is our formula for the standard geometric summation, where we have s, basically a1 through an, all being added up to form Sn. Now, the infinite summation has a couple of prerequisites. So obviously, what the infinite summation itself means is that n, the total number of values we have, is going to be infinite. So that means that we cannot theoretically calculate r to the power of infinity unless, oh, sorry, there's no prerequisites listed here, unless r is between -1 and 1. Only if r is between -1 and 1 can we make sure that r to the power of infinity is not going to be divergent. It's not going to go to infinity or negative infinity or oscillate somewhere in between. What it's going to do is it's going to go to 0 because the number is less than 1. And what this allows us to do is that if we, we could either use a limit if you have learned limits, or we can simply reason it out by saying that we are inputting infinity in place of n, and since r to the power of infinity must be 0, we end up with this final formula, which is very, very simple. And this is going to basically allow us to conduct the later operations of this problem. There's a couple of other sample problems that I'd like you to go ahead and maybe pause the lecture if you'd like, to go ahead and solve. So basically, number 1 says a patient receives repeated doses of a drug. At each time the drug is administered, there's a 5% chance that the patient will be cured. What is the probability that the patient will be cured within 20 successive doses? Again, this is a very simple kind of inputting the numbers sort of problem. Obviously, there's a 5% chance that the patient will be cured, and we do want to find the probability that the patient will be cured, which would indicate that the common ratio, R, is 5%, or 1 over 20. And since we're doing it over 20 successive doses, we know that there's a limit of 20 successive doses that we're going to get, which means that N is going to be 20. Whoops. And basically inputting these numbers should allow us to get the answer. Meanwhile, this is a more fun problem, I would say. It basically says that A, B, and C are fighting a 3-cornered pistol duel. Standard duel, it's a triangle. They stand, each person stands on one corner of the triangle, and then they try to shoot each other. Everyone knows that should each player aim to kill, A's chance of hitting his target is 0.3. C's is 0.5, and B never misses. He's the best shot out there. Now, the 3 duelists are going to fire at their choice of target, so they can only choose one person to fire at, in succession, cyclically, in alphabetic order until only one man is left standing. What this means is that A is going to start by firing at, either C or B. Should he aim to kill. And then B is going to fire the same way, aiming to kill A or C. And C is going to fire in the same way. And then we go back to A and we cycle through the alphabet infinite number of times until only one man is left standing. So theoretically, should, for example, B get shot and A and C aim to kill each other, there is an infinite number of pistol shots that can happen until one of them dies, since either of them could, suddenly have a stroke of bad luck and miss the rest of their shots for, eternity. So what should A's strategy be? This is a somewhat popular question. You might have heard of it before. Some people have called it a trick question, but A's best chance is to basically deliberately miss, to fire his pistol shot at the ground, followed by firing at B. The reason for this is, and I can't go into the details too much here because the calculations are actually quite complicated. If A, for example, should choose to kill C, he has a 0.3 chance of doing so. And if he manages to kill C successfully, what that will mean is that B will instantly shoot A and win the duel. So meanwhile, if A should miss C with a probability of 0.7, what B will do is, given that everyone is thinking logically, what this problem assumes is that B is going to fire at A. B is going to fire at C rather than A, since C has an accuracy of 0.5 and A has an accuracy of 0.3. And basically, given that B is going to shoot C with 100% accuracy, C is going to die, and then A has the chance of duking it out with B. But what the deliberate miss does here is it eliminates the chance that A accidentally kills C and B basically shoots A in response, leading to B automatically winning. So if you do the deliberate miss, the chances that B will kill C is automatic. C is basically has received a death sentence. And then A has the chance to fire at B first and try to duke it out with B. Meanwhile, obviously, the answer to the first problem, if you punch the numbers into your calculator, it should have been something like 0.641514. Therefore, the patient approximately has a 64.2% chance of success, which is not terrible. So let's do the proof. Basically, setting up the proof is not difficult. Basically, what setting up the proof involves is inputting all of the numbers into the original binomial probability formula. And then what we can do is we can use the arithmetico-geometric sum method. Now, again, the dictates of the presentation say that presenting the actual proof here is quite difficult. But basically, and this is the original method that I used to solve this problem as part of class. Basically, what this does is you use what I like to call the grid of infinity, which is double infinite sum. You basically line up the different values over here like so, and then you basically what you do is the geometric sequence continues along this line, and then you multiply by the common ratio each time. The geometric sequences continue. Basically, you have an infinite number of infinite geometric summations, and then you add them vertically, which gives you a simple geometric sum that is calculable using the above formula. Now, what is special about the original sum, however, is that this arithmetical part exists. The reason for that, obviously, is the expected value is NP, not just P. So you have to multiply N each time. And since we're looking for the expected value of numbers, of the number of dice rolls, N is going to have to be multiplied to the start of the equation, which means that we cannot compute the actual answer just using the arithmetical geometric sum like a geometric summation. However, there is another approved method that I must admit is a lot easier. It's basically the classic geometric summation trick where you multiply it with a common ratio and then you subtract instead of adding. I urge you to try it all, but basically this yields a nice complete answer without having to bother with the kind of like doubly infinite nature of the other solution. You can also solve it using induction. I have seen people do this, and it's not hard. It's just the inductive proof is quite rigorous. So, you know, if you want to test out your logic skills, I recommend that you do this. And meanwhile, we can also generalize this problem by substituting in a couple of variables. So we can say that the number of trials, for example, is n rather than 6. The probability of success is p rather than 1 over 6. The probability of failure is q rather than 5 over 6. And the outcome, getting a 6, is instead substituted as event A. Now, this leads us to the theorem that is basically going to be the centerpiece of this presentation, and that is that given repeated random trials of a sample space, including some outcome A, with probability P is greater than 0, NP equals 1, where N is the expected number of trials required to yield the first instance of A. So what this means is that this is applicable to any other probability sample space out there. So for example, if I'm rolling a 20-sided die instead of a 6-sided die, if I'm rolling a 20-sided die, the probability, no, not the probability, the expected number of trials required to yield, say for example, a 1 is going to be 20 because that's the reciprocal of 1 over 20. And now we know that NP equals 1. Obviously, you can substitute the variables into the proof, thereby allowing you to prove this without going back to the original proof and attempting to redo it. Now, there's an extension to this problem, which is also from 50 Challenging Problems in Probability. This is question 14, and this is called Lucky Cereal. Basically, what this problem entails is that coupons in cereal boxes are numbered from 1 to 5. A set of 1 of each is required for a prize. With 1 coupon per box and an infinite number of boxes available, how many boxes on average are required to make a complete set? Now, the problem sounds quite simple. It's basically how many times you need to buy the cereal box in order to get all 5 types of coupons. But in practice, it's actually very hard because many of the geometric summation methods that we've learned previously are not applicable to this problem. What we can do, however, is we can look at the previous theorem that we established and use it to basically segment the problem into 5 different components. What this allows us to do is we can basically, the first box we pick out, we will get a unique coupon no matter what, right? And from then on until we get the next box, the probability that we will get a unique coupon is 4 over 5. Since, for example, if we drew a 1 on the first box, the remaining coupons are valid, but if we get another 1, that's not really helping us get to the prize. And then once we find the second distinct coupon, the probability will be 3 over 5. If we find the third one, it'll be 2 over 5, and so on and so forth. Now, what that means is that we can basically establish that the required expected number of cereal boxes is going to be the reciprocal of each probability. So what that entails is that we can basically flip each probability. So since the first probability is 1, we can flip 1 to get 1. Since the second probability is 5 over 4, we can flip that, 4 over 5. We can flip that to get 5 over 4, and then we can flip the third one to get 5 over 3, and the second one to get 5 over 2, and et cetera, et cetera, et cetera. And that leads us to the final answer, which is about 11.42 boxes. And we can also generalize this to all coupons from 1 to n. This requires a harmonic sum, which is outside the scope of this actual presentation, but it's basically an ancient formula proved by Euler. So go ahead and look it up, the harmonic sum formula. It will prove a little bit complicated to use in practice, but I think this is mathematically very valid. And basically what this means is that the harmonic sum within of itself is basically what we've just done. The reciprocals of all of the numbers. In this case, we've multiplied them by 5, and we're basically adding all of them. In this case, we would have n coupons, distinct coupons rather than 5, as we have here. And then there's a different scenario, which is the deck of cards. This problem, a standard deck of cards is 52 cards, 4 of which are aces. On average, how many cards must be drawn off the top of a standard deck of cards before the first ace is drawn? And note that this total does include the first ace. So if you look at this problem, initially it looks like the original problem that we had, which is about rolling a dice. You roll a dice, or you pick a deck card out of a card deck. What's the difference? Well, the difference is here we're drawing off the top of a standard deck. What that implies is that we do not have replacement. It's not that we pick the card off the top, we look at it, if it's not an ace, we put the card back on top of the deck and we shuffle it again. That's not what's happening. Instead, what we're doing is we're taking the card, looking at it. If it's not an ace, we're setting it aside, and then we're taking a look at the next card and the next card. What that means is that this is sampling without replacement. Which means that it's basically not a binomial distribution at all. So how on earth do we go about solving this? Well, thankfully, if you actually try and compute the probability of each, it turns out that the factorials manage to cancel each other out. Again, this was going to be a proof, kind of like a concluding proof of the presentation, but again, the technological requirements are a little bit iffy. But this problem is really engaging, and obviously, if you like to play cards with your friends, which I do, I recommend that you do calculate this probability just so that you, hopefully it'll help you get better odds in your games. But basically, the average is actually a clean 10.6 cards. I actually anticipated some sort of infinitesimal, so this was pleasantly surprising. It is 10.6 cards, but honestly, I recommend that you try to prove this problem. The factorials cancel each other out. You will have to use a calculator. I recommend Wolfram Mathematica to calculate the final sigmas, but it is possible because we do have exponential sigma formulas for everything. So yeah, just try and calculate this. And finally, what I feel about this and this problem in general is that it's not necessarily a branch of mathematics that's common to, common math classes. But when you really try to explore kind of the depths of probability and what you can do with these different concepts that you learn about in class, these are not terribly advanced concepts, especially when you get to the high school level. Almost everyone will learn these concepts in some form or shape. What's important is that we maintain vigilance, mathematical vigilance, where we look at these concepts and then we manage to apply them to unique situations like this where we don't necessarily have a formula, and then we establish theorems that can help us solve more advanced problems like the deck of cards or the lucky cereal. And, I hope that this serves as a good example of a mathematical exploration for you all, and I wish you good luck. Thank you.